In computer science, a smart pointer is an abstract data type that simulates a pointer while providing additional features, such as automatic memory management or bounds checking. These additional features are intended to reduce bugs caused by the misuse of pointers while retaining efficiency. Smart pointers typically keep track of the memory they point to. They may also be used to manage other resources, such as network connections and file handles. Misuse of pointers is a major source of bugs. Smart pointers prevent most situations of memory leaks by making the memory deallocation automatic. More generally, they make object destruction automatic. The object controlled by a smart pointer is automatically destroyed when the last owner of the object is destroyed, for example because the owner is a local variable, and execution leaves the variable's scope. Smart pointers also eliminate dangling pointers by postponing destruction until the object is no longer in use. Several types of smart pointers exist. Some work with reference counting, others by assigning ownership of the object to a single pointer. If a language supports automatic garbage collection, then smart pointers are not needed for the reclamation and safety aspects of memory management, but are nevertheless useful for other purposes, such as cache data structure residence management and resource management of objects such as file handles or network sockets. C++ smart pointers. In C++, smart pointers may be implemented as a template class that mimics, by means of operator overloading, the behavior of traditional pointers, while providing additional memory management algorithms. Smart pointers can facilitate intentional programming by expressing the use of a pointer in the type itself. For example, if a C++ function returns a pointer, there is no way to know whether the caller should delete the memory pointed to when the caller is finished with the information. Traditionally, this has been solved with comments, but this can be error-prone. The potential problems associated with this use can be mitigated by instead returning a unique PTR. The function makes explicit that the caller will take ownership of the result. Furthermore, no memory will be leaked if the caller does nothing. Prior to C++ 11, unique PTR can be replaced with auto PTR. Creating new objects, in order to ease the allocation of a C++ 11 introduced. Similarly since C++ 14.1 can use. It is preferred, in almost all circumstances, using these facilities over the new keyword, unique PTR. C++ 11 introduces STD Unique PTR, defined in the header memory. A unique PTR is a container for a raw pointer, which the unique PTR is said to own. A unique PTR explicitly prevents copying of its contained pointer, but the STD move function can be used to transfer ownership of the contained pointer to another unique PTR. A unique PTR cannot be copied because its copy constructor and assignment operators are explicitly deleted. History: STD Auto PTR is still available, but it is deprecated under C++ 11. The copy constructor and assignment operators of Auto PTR do not actually copy the stored pointer. Instead, they transfer it, leaving the previous Auto PTR object empty. This was one way to implement strict ownership, so that only one Auto PTR object could own the pointer at any given time. This means that Auto PTR should not be used where copy semantics are needed. Since Auto PTR already existed with its copy semantics, it could not be upgraded to be a move-only pointer without breaking backwards compatibility with existing code. Shared PTR and Weak PTR. C++ 11 introduces STD Shared PTR and STD Weak PTR, defined in the header memory. A shared PTR is a container for a raw pointer. It maintains reference-counted ownership of its contained pointer in cooperation with all copies of the shared PTR. The object referenced by the contained raw pointer will be destroyed when and only when all copies of the shared PTR have been destroyed. A weak PTR is a container for a raw pointer. It is created as a copy of a shared PTR. The existence or destruction of weak PTR copies of a shared PTR have no effect on the shared PTR or its other copies. After all copies of a shared PTR have been destroyed, all weak PTR copies become empty. Circular references. Because the implementation of shared PTR uses reference counting, circular references are potentially a problem. A circular shared PTR chain can be broken by changing the code so that one of the references is a weak PTR. Concurrency guarantees, multiple threads can safely simultaneously access different shared PTR and weak PTR objects that point to the same object. The referenced object itself needs to be protected separately to ensure thread safety. History: shared PTR and weak PTR are based on versions used by the Boost libraries. Tier 1 first introduced them to the standard, but C++11 gives them additional functionality in line with the Boost version. See also: resource acquisition is initialization, auto PTR, opaque pointer, reference. The Boost library includes Boost intrusive PTR, a reference counting and intrusively counted smart pointer implementation for C++. References: Sutter, Herb. Trip Report, ISO C++ Spring 2013 Meeting isocpp.org. Retrieved June 14, 2013 AB ISO 14882 2011 20.7.1, Cert C++ Secure Coding Standard, Boost Shared PTR Thread Safety, http www.boost.org libslips Intrusive PTR HTML, external links, sample chapter Smart Pointers from the book Modern C++ Design, Generic Programming and Design Patterns Applied by Andrei Alexandrescu, Addison Wesley, 2001. Code example COUNT PTR HPP from the book The C++ Standard Library, a tutorial and reference by Nikolai M. Josutis, Boost Smart Pointers, article The New C++ Smart, Pointers by Herb Sutter August 1, 2002, Smart Pointers, What, Why, Which? By Yonat Sharon, Smart Pointers Overview by John M. DeLagos, The Jasper Library Yet another smart pointer implementation in C++, Smart Pointers in Delphi, Smart Pointers in Rust,